Okay. So this is for mostly quotient rule, but a little bit chain rule, a little product rule too in this one. This one was very simple product rule. The way that this works is that you have your numerator and you take its derivative, which in this case would be negative 15. And you have a denominator. So you take its derivative, and its derivative would be 2x plus 2. And then you always lead off with the denominator for y prime. Y prime being your derivative. So it is the denominator, which is x squared plus 2x, times the derivative of the numerator, which is negative 15, plus your numerator, which is negative 15x, times the derivative of the denominator, which is 2x plus 2.
Professor?
Yes.
I thought on the quotient rule was subtracted.
Oh, you do. I'm sorry. Very, very sorry. Thank you. Yes, you do subtract. Thank you, Ashley. 1 point for Ashley. Take my note right up there. And then the bottom is always your denominator as it was in the original problem, but it's squared. And that's as far as you have to go. You don't have to go any further than that. Now, yes, it is possible to. Yes, you can clean it up, and yes, it'll look a whole lot nicer. But this was the calculus. The cleaning up part is algebra. And right now, I want just the calculus. I want to make sure you can do the calculus part. So for the second one, we need h prime of u. And so that I won't forget, I'll be sure and get negative this time. So in my numerator now, I have, let's see if we can blow that up a little so you can see better. In my numerator, I have 3u squared minus 8. So the derivative of my numerator is 3 times 2 is 6u, and the derivative of minus 8 is 0. And then I have my denominator, which is 6u. And the derivative of 6u is simply 6. So then I always lead off with my denominator, which is 6u, times the derivative of the numerator, which is also 6u, minus my numerator, which is 3u squared minus 8, times the derivative of the denominator, which is 6, and that's over the denominator 6u, which is squared. And that's all you have to do. You're done. So then p prime of t is going to be a similar process. The numerator is 10.43 t cubed. So let's see. Might need a calculator for that one.
31.29.
Okay, thank you. Yes, that'll save me some time. So this is the numerator, but n prime is going to be 31.29 t squared plus 4 times 2 is 8t. And then my denominator is t plus 3, which means its derivative is really very easy. It's just 1. So my derivative of p prime of t is t plus 3 times 31.29 t squared plus 8t minus 10.43t cubed plus 4t squared times 1.
So it looks like it's gonna come out to 0, but it's actually the.
Say that again?
Well, that's where I kind of forgot. One is like, well, I can't take the derivative of 2 plus 3. So I'm just putting 0
It's 1. The derivative of 3 is 0, but the derivative of t is 1. Its coefficient is 1.
Okay.
Okay? And then your denominator then, of course, has to be squared. So that's t plus 3, and that's squared. Now, number 4 is a product rule. So I'm going to wait and do it at the end. So number 5, our numerator is negative 6x to the 4th plus 5x squared minus x, and its derivative is negative 4 sixths is 24x to the 3rd plus 2 times 5 is 10x minus 1. And then our denominator is 2x squared plus 3, minus 3. So when we take its derivative, that's 2 times 2 is 4x, and then the derivative of minus 3 is 0. So that's just going to be 4x. So y prime, going to have a big long numerator, is going to be 2x squared minus 3 times negative 24x cubed plus 10x minus 1 minus, whoops, trying to get away, negative 6x to the 4th plus 5x squared minus x times 4x, and the denominator is going to be 2x squared minus 3, and that quantity is squared.
Now, if there was a parentheses anywhere in the numerator, that would change things, right?
If there had been parentheses here,
Yeah.
anywhere in there, yes. So then back up here to number 4. Number 4 is a product rule. So number 4 looks like this. X plus 5 times x minus 4. And the product rule, since this is y, product rule says take the derivative of the first factor, which would be 1. Take the derivative of the second factor, which in this case would also be 1, and then trade their derivatives with each other. So this is going to be x plus 5 times 1, and your product rule is plus. And then your second factor is x minus 4 times the derivative of your first factor is 1, and you're done. So really it's just in this case, the derivative of the product is the sum of the two factors. That's because the derivatives of each factor was just 1. Okay? So hopefully everybody did well on that one. The next one probably will be mixed up. I'll give you some chain rule problems along with maybe a product and a derivative. So just keep practicing. Oh, I've got way too many of these. That just means you'll do better on the test. Now, if I have my notes correctly, I finally got them somewhat organized, so I hope I do. This is where we should be. We were working on the chain rule, and we stopped. I hadn't yet done example 7, so let me look back and see if we need to rehash any of the others. So we had done example 5 and 6, and we're ready to do example 7. So just to give a reminder, when we have chain rule, and maybe we want to start out with the chain rule part of this. When we have chain rule, we have to look first at the whole function, and what we see in this whole function is that we also have a product. So this is factor 1, and the derivative of 4x is just 4. And then we need the derivative of the second factor, but the second factor, we're either going to have to use a product rule and break this up into 3x plus 5 times, and that would not be much fun because we'd have to do the product rule several times on that one. So instead we're going to use chain rule. And what the chain rule says is that you take the derivative of the outside, ignoring what's in the parentheses. You take the derivative of what's inside, of the outside, and the outside is something raised to the 5th power. So the way we take that derivative is we drop that 5 down in front of the parentheses, because this is just straight power rule. Then reduce the power by 1, but then we have to take the derivative of what's inside the parentheses. And what's inside the parentheses is 3x plus 5. So the derivative of 3x plus 5 is 3. So what the chain rule tells us is the derivative of our second factor is 5 times 3x plus 5 to the 4th power times 3. And this is one of the few times it might be easier as you go forward to actually straighten it up a little bit by multiplying your 5 times your 3. Because it'll just make it easier to keep up with. So this was the chain rule part. Now we go to the product rule part. And the product rule says you take your first factor, which is 4x, and you multiply by the derivative of your second factor, which is this 15 times 3x plus 5 raised to the 4th power. And then you add your second factor, which is that 3x plus 5 raised to the 5th power, times the derivative of your first factor, which is 4. And it doesn't matter if you put the 4 behind or if you put it in front. That's up to you. Now you can simplify beyond that, but you don't have to. Your calculus is actually done at that point. Okay? So remember, even though we had a product rule problem, one of our derivatives required us to use the chain rule. So even though the rules, each rule in itself is not a hard rule to learn, but it's hard sometimes to recognize which ones you need to use and to realize that you need to use more than one rule on the same problem. Okay, and the only way to do this is just practice, practice, practice. anybody have any questions about this one before I go on?
On the test, when you say use the chain rule, or you have to look for certain factors.
You have to look. You're gonna have to look. Now, notice even on these quizzes I'm giving you, I tell you verbally that's what this quiz is on. But after a while, I'm not gonna be able to tell you that because I'm gonna hand you a quiz that has 6 different kinds of problems on it. And every one might be different. So just practice and learn to recognize it.
What's the best way to look at the higher powers?
The best way to know when you've got chain rule is you're looking for anything that has a radical with more than one term under it. Look for a set of parentheses with more than one term inside them. As we get further along in the exponential and logarithm parts, you'll look for where you have an exponential function where you've got more than one term in the base. Or you'll have a logarithm of something that's more than one term, so you'll know that you have a chain rule problem. Product rule problems, you have to look and think, okay, if I was doing this problem, if I wasn't really doing calculus, if I wasn't looking for a derivative, what would I do to simplify this problem? Is there something I would do to simplify this? And if I were looking at that problem, I'd say, well, you know, if I was going to try to simplify that, I need to distribute. Well, you distribute when you have something that's multiplication. Or if you've got something that's a quotient rule, you're looking for a fraction, basically. You're looking to find a fraction. So you know you have a quotient when you have a fraction, and there's more than one term in the denominator. There may be only one term in the numerator, but for it to be a quotient rule problem, there has to be, most of the time, more than one term in the denominator, or maybe some kind of an expression in the denominator, not just a number, or not just like an x. Because if you've got just an x, you can always raise that x to -1 power and bring it up to the numerator. Okay? I'll try to give you some good practice sheets for these because I know that's really the only way you can learn these. Now, once again, this is not my favorite notation for a derivative, but it is legal notation for a derivative. D sub x means take the derivative of. So d sub x in this case. Now you help me analyze this because this is what we were just talking about. What kind of rules do I need here?
We need the quotient.
That's right, you need a quotient rule because you have a numerator and you have a denominator, and the denominator is x minus 1, not just, you know, a number, but it's actually an expression. So you need quotient rule. Okay, and it might help you as you're doing these to actually write down what rule you're using. But when you start getting into doing your derivatives for your quotient rule, as we're going to do right now, taking the derivative of your denominator, no problem. Then you get to your numerator. And your numerator is 3x plus 2 raised to the 7th power. And immediately that should tell you, I've got more problems here. I have to have a quotient rule. I'm sorry, not a quotient rule, a chain rule. So if you write yourself notes as you go along, it'll help you backtrack in case you need to backtrack and look for any mistakes or to know what you did later on. So then I know to get n prime, I'm going to have the chain rule, which says that I take my power on the outside of the parentheses, drop it down in front of the parentheses, and reduce it by 1. Then I take what's inside the parentheses and take its derivative. The derivative of 3x plus 2 is 3 plus 0, which is just 3. And then I put back what's in the parentheses. I don't worry about it until after I've taken its derivative, then I put it back in. And then if you want to simplify it, since you're going to have to use it again, then it's okay to do that. Go ahead and say that this is 3 times 7 is 21 times 3x plus 2 to the sixth power. That way you don't have as much to write when we have to come down here and use it in the quotient rule. So now we're ready to do quotient rule. And we know quotient rule begins and ends with a quotient. And we start off in the denominator with x minus 1 times the derivative of the numerator, which is 21 times 3x plus 2 raised to the sixth power. And then we're going to subtract the numerator, which is 3x plus 2, in parentheses, and raised to the seventh power, times the derivative of the denominator, which fortunately is very small, it's just 1. And it's all over the denominator, x minus 1 squared. Now, I will tell you that when they do these in the book, something that they're going to do, and since I know some of you are looking at those simplifications, what they'll do after they've kind of cleaned all of this up is they'll actually factor out 3x plus 2 raised to the sixth power in the numerator. I don't know why they do. It doesn't make any sense because it doesn't let you cancel anything in the denominator, but they'll do it. I don't require that you do that. But if you see them doing some big long algebraic thing and you see this show up on the outside of the set of parentheses, well, that's why. They've simply factored it. Does anybody have any questions on that one? Yes.
The 21, 3x plus 2
Mm-hmm.
What did you multiply that?
I multiplied this 7, which came from the power, and this 3, which came from what was inside the parentheses.
Multiply that by the derivative.
It's part of the derivative, okay? Because this has this derivative, and then the 7 in the front is from bringing down your 7 and then reducing your 7 by 1. So it's easier to keep up with this 7 and the 3 if you'll just mush them together, so you don't have quite as many sets of parentheses to write,
All right.
okay? That's the only algebra, or only simplification I'm going to do is enough to make my life easier when I get to this part. I don't, you know, we could probably multiply that out, but I wouldn't want to. That'd be a lot of work. Okay? Any other questions? Okay, let's take a look at a revenue problem. I have a problem here. Should be in your notes. The revenue realized by a small city from the collection of fines from the parking tickets is given by this function, where N is the number of work hours a day that can be devoted to parking patrol. It says at the outbreak of a flu epidemic, 30 work hours were used daily in parking patrol, but during the epidemic, the number is decreasing at the rate of 6 work hours a day. How fast is revenue from parking fines decreasing at the outbreak of the epidemic? Now that all sounds pretty complicated, so let's try to take this apart a little bit at a time. This is a revenue function. The revenue function is money, okay? R of N is money. N is the number of work hours. Basically, it's the number of, they call it work hours because it isn't simply the hours worked by a single person. It's the number of hours worked every day by a group of people on parking patrol. When they had the beginning of the flu epidemic, 30 work hours were used daily in parking patrol. But during the epidemic, it was decreasing at 6 work hours a day because people were getting the flu and they weren't coming into work. So it says, how fast is revenue from parking fines decreasing at the outbreak of the epidemic? Okay, so we know the revenue is actually going down. How fast? How fast is a rate of change? we know that rate of change in our common everyday language means slope. And we know as soon as we see rate of change and we see slope, that means take a derivative. Okay? Because it says at the outbreak. Okay, at the outbreak. So we're looking at a particular moment in time. So the first thing we're going to do is we're going to have to take the derivative of that fairly innocent looking function. And it turns out it's not too hard. So our derivative is going to be what kind of rule do we need?
Quotient.
We need a quotient rule. So that means we're going to take the derivative of the numerator, because we know the numerator is 8,000n, and its derivative is 8,000. And we know the denominator is n plus 2. And that denominator has a derivative, thank goodness, of just 1. So it looks like maybe this derivative is not going to be too bad. So now we're going to take the derivative, which is going to be r prime, or dr over dn. And we know, because it's quotient rule, that we're going to wind up with a quotient. We know we're going to be subtracting in the numerator, and we know we're going to be making a square in the denominator. So that's all the quotient rule. We just need to fill in the pieces. So the pieces are, we lead off with the denominator, n plus 2, times the derivative of the numerator, which is 8,000, minus the numerator, which is 8,000n, and times the derivative of the denominator, which is just 1, over n plus 2, quantity squared, because that's part of the derivative rule. Now, that doesn't look too bad in itself, but since we're going to have to actually do some numerical work, we might want to try to clean it up a little bit. So let's see if we can make it look a little bit better. So we've got 8,000n times 1. Well, that's minus 8,000n. And then we've got n plus 2 times 8,000. So n times 8,000 is 8,000. n plus 2 times 8,000 is 16,000. And that's all over this same denominator. But we can see that that might actually be a little bit neater even than that, because we have 8,000n minus 8,000n is going to disappear. And when that disappears, then what we have for our r prime is just simply 16,000, big difference that extra 0 makes, over n plus 2 squared. So there's your derivative. Okay? We all good with that?
So what would you plug in to actually get an answer?
Well, that's what we're going to do next.
Oh, okay.
First, we had to get the derivative. Now, at this point, how fast is revenue from parking fines decreasing at the outbreak? Well, it didn't start decreasing until this outbreak happened, and at that point it's decreasing at 6 work hours per day. Okay, so let's say on day 1 it decreased by 6 work hours a day. Excuse me?
No, we're doing 24 hours.
Yep, Well, but within one day, the first day. So what we would do, since it's decreasing at that rate, is we're gonna set this equal to 16,000 over, let's see, we would actually set this equal to -6 and determine what it was on that day, what the number of work hours was if we needed to. But actually, when they ask us how fast is revenue from parking fines decreasing at the outbreak, that's pretty much all they're asking us, is to find the derivative of it. They're not really asking us for much of anything else. Now, just to be sure I haven't overlooked anything, let me pull up the PowerPoint and make sure I didn't leave out any problems, because this has been a week. And if we are finished, then we'll go on and do exponential functions.
It says there's an example.
Yeah, that's what I was thinking, and I'm not seeing it in my notes, and I would have sworn there was one. Oh, okay, there it is. It is. So I do have example 10. Oh, okay, and yes, they did go ahead. Go ahead and finish this one up. So it says, since 30 work hours are used at the outbreak, they use n equals 30. So in our derivative, we replace n with 30, so at the beginning it was 30. And then we have 16,000 over 30 plus 2, quantity squared, comes out to be 15.625. And the derivative, which is the derivative of the work hours with respect to time, is -6. So, stop that. So what we do is we replace the derivative of the revenue times the derivative of the, that we're given in the problem where it says it's decreasing by 6 hours a day. And since we're actually looking for revenue, what this is giving us is $15.63 roughly per day. It was decreasing on that day, and it's decreasing by an additional $6 every day. So the actual complete decrease is going to be $93.75. So revenue is being lost at about $94 a day at the outbreak of the epidemic. Now, does that part make sense? Does everybody know where that came from?
Well, let's see. What happened if the derivative was
Okay, let's go back to the problem statement.
but I think it has to do it that way since it says decreasing. But-
Yes, it is decreasing.
So I get it, that's why I'm placing.
Yeah, it's a little, it's in the wording, it's a little difficult to decipher the wording. So what the derivative is giving us, what this is giving us, is this is telling us that this is the derivative of the revenue function. So sometimes this derivative is increasing, sometimes it's decreasing, it just depends on what the value of n is, okay? But they do tell us that at the beginning of it, they were using 30 work hours a day. So if they were using 30 work hours a day at the beginning, then our prime for 30 work hours a day is going to be 16,000 divided by 30 plus 2 squared, which is where that 15, what was it? 15,625. Okay? So it was decreasing from this beginning point, and then it says that during the epidemic, the number is decreasing at the rate of 6 work hours a day. And since this is the cost of one day, this is $15.63 per day. Because remember, this is a derivative. Okay?
Yeah, I'm there, that's really, yeah.
And then this is how much each day, how many work hours each day. So you're gonna have to multiply this times the -6 for each additional day. So that's about $94. Okay?
So it's $94 a day.
Right. At the outbreak. Now, if they hadn't given us this information here, we couldn't have actually come up with the total amount. We had to know that much. I'm guessing the 6 work hours a day was from somebody being out sick. That person probably did parking patrol 6 hours a day. So then probably the next day it was 12 because there were 2 people out sick, and so forth, until finally it would start leveling out. Okay, another application of it that's, it's an interesting application, even though sometimes I wonder why we need calculus other than to explain what we can do algebraically. Does everybody remember compound interest, your good friend compound interest back in Math 1630? Calculating compound interest with a compound interest formula?
So I have a question.
Yes.
Are we gonna be taking our test on Tuesday?
No.
Is it gonna be like Thursday or?
We haven't finished the last 2 sections yet, so it'll be at least a week, okay? At least a week.
Thank you.
I can adjust chapter 13 and 14 to cover fewer topics. I want to make sure you get chapter 12. Chapter 12 is the core of this course.
Okay.
Okay, so example 10 says, suppose a sum of money, and this should sound familiar to you. Suppose a sum of money is deposited in an account with an interest rate of R% per year, compounded monthly, and at the end of 10 years, the balance in the account is given by 500, which is your principal, times 1 plus the interest rate over 1,200, 1,200 being 12 months times 10 years, raised to the 120th power for the once a month compounding for 10 years. And it says they want us to find the rate of change with A with respect to R, and then if R equals 5 or 7. We're going to come back to that. What we need is the rate of change. And when it tells us find the rate of change, that means find the derivative. So find the derivative of A, find A prime. What kind of rule do we need to find A prime? Yeah, it looks like we need a chain rule. We don't really need a quotient rule for this because we can rewrite it so that that's 1 over 1,200 as a fraction, so that we don't really have to use a quotient rule, and that would be good. So we have A is actually 500 times 1 plus 1 over 1,200 R raised to the 120th power to actually make it easier to take the derivative. Now the 500, remember, is not a function. It's a coefficient. It's a multiplier. And anytime you have a multiplier or a coefficient of something, it just hitchhikes along through the problem. It's just a hitchhiker. So we're just going to keep the 500. But then we have to take the derivative of this. So to take the derivative of that, we need chain rule. Chain rule says bring the 120 down in front, keep what's inside, reduce the 120 by 1, and then take the derivative of this. And the derivative of 1 is 0, and the derivative of 1 over 1200R is 1 over 1200. So it made it all look ever so much worse than what it actually is going to be. So what we have in here is still 1 plus, and now I'm going to put the R back over 1200 because we may as well. It's easier to write. Now, as far as cleaning all of this up, because this is going to look a lot better if we clean it up a little bit. What we're going to do to make it look a little bit better, this is all cosmetic and it's all algebra, this was the calculus, we're done with the calculus, is we're going to take these constants, since this is all a big huge multiplication problem, we're going to take that 1 over 1200 and that 120 and that 500, and we're going to multiply all those together. And then we're going to keep what's in the parentheses and leave it alone. So let's see what that number in the front is now. And it turns out to be just 50. So A prime, the derivative is 50 times 1 plus the interest rate divided by 1200 raised to the 119th power. And then it says find the rate of change if R is 5 or if R is 7. So all we're doing is plugging in 5 and plugging in 7. And if I'm going to do that arithmetic, frankly, I'd rather use the calculator. So I'm going to take this function and since I don't want to type it in 2 or 3 times, I'm going to type it in Y1, 50 and then parentheses 1 plus another set of parentheses, the interest rate, which will be X, divided by 1200, close those parentheses, then close the whole expression parentheses and raise it to the 119th power. And then you can either go to the home screen or you can set your table up and have it ask. So if we go to the table now, if I say, what if X is 5, because 5 is my interest rate, and it says, well, it's $82 and less than a penny. Not a penny. And if it's 7, then it's $99.90. Almost $100. Now what does that mean? What that means is that when your money's been, if your money is in there at an interest rate of 5%, that the future value of your money is changing at $82.01 per day. That's how fast it's accumulating interest, basically.
Isn't it monthly?
Monthly, yes, thank you. And then if R is 7, if you raise the interest rate to 7, look how much faster your money is actually accumulating value. Your initial deposit is actually accumulating almost an additional $100 a day if the interest rate, or not per day, but per month, if your interest rate is 7%. So what the derivative of the compound interest formula is telling you is how fast at each compounding period, how much per compounding period, what's the rate of change at various interest rates? How fast is your money increasing? Now, if you want to be realistic about it, let's see, compound interest right now is what? Maybe 1%? I think that would be generous because usually that's a CD. So much less, about $55.21 a month. Oh, and that's over the course of the life of the loan. That's where it's changing over the life of the loan. And you can see here that since this is the values of R, notice that your compound interest amount goes higher and higher and higher as your interest rate goes higher. So we are finished with the chain rule. I'll go ahead and tell you a little bit about the exponential functions, but we're not going to go much into it, so that you'll be able to kind of look ahead. But we're going to need Tuesday next week to do exponentials and Thursday to do logarithmic functions before we can go on and have a test over chapter 12. Now, I had some of you for Math 1630 and some of you I didn't. How many people have fond memories of logarithms and exponential functions? Anybody? Even if you were in my class? It's okay if you didn't like them. I didn't like them either. Most of the time people don't like those functions because they have all these rules you have to memorize. You're going to see that we don't have that many rules to memorize for what we're going to do here. Let me get the PowerPoint and just show you the first example and then we'll go. Well, actually, I don't need the PowerPoint to do that. I've got my handout with the first one on. Because remember, we're just learning how to take derivatives of these things. We're not trying to simplify them. Why do I have logarithmic functions, not exponential functions? Ah, here they are. For the derivative of exponential functions, which is what we're going to look at first. There's your rule. Now, what does that rule say in English? It is the same thing. If y is e raised to the x power, e being the natural log function, then it's its own derivative. It's its own derivative. It's the easiest one in the world to take. if you have the natural exponential, if you have the e, or the e to the power function, then it's its own derivative. Now, the only way that this problem changes is if we have e to the 5x, this becomes a chain rule problem. Because the power is a function. So that means that the only thing we have to do to take this derivative, y prime, we know that this is its own derivative. But since its power is a function, we need to take the derivative of its power. And its power's derivative is, what's the derivative of 5x? 5. Okay? That's it. Now, rather than going on to the other examples, I'm going to stick with this one for a couple of minutes because we've only got a few minutes and I don't want to spend a lot of time and then throw a curve at you. So, suppose this function had been y equals e to the 7 plus x squared power. What's the derivative? What's the exponential derivative tell you it starts with? E to the 7 plus x power. Or 7 plus x squared. Now what do I need the derivative of?
7 plus x.
Okay, and what's that derivative? 0 plus 2x. So it's 2x e to the 7 plus x squared power. Okay? What if I have y equals e to the square root of x? Okay. What's the derivative of the square root of x? Exactly. The only reason I bring it down in front is because it kind of looks better than it does stuck out there after the power, and you're sure where the power ends that way. Okay? So your exponential rule is not going to be tough. The only thing that's going to be a little bit different is when the base is not e. When the base is some other number than e. And I'll explain that to you next week when we get back on Tuesday. So right now, get caught up on sections 12.1 through 4. Practice taking derivatives on 12.1 through 4. We will finish up next week and have a test a week from Tuesday. Okay?